Antimatter is a volatile, incredibly rare substance, usually forged in the universe's most extreme, high-energy events. We're talking about the aftermath of exploding supernovas, or the intense, sudden bursts of lightning strikes. This scale shows just how rare it actually is. Because it is so intensely difficult to produce and contain, a tiny 1-gram unit holds an estimated price tag of $25 billion. It is the single most expensive material in existence. You don't need a particle accelerator or a dying star to find it, though. You just need to walk into your kitchen. Sitting right there on the counter, the ordinary banana is continuously emitting this exact same exotic substance. If a common piece of fruit is naturally producing the most valuable material on Earth, it raises an obvious economic question. Why haven't we industrialized bananas into a highly lucrative antimatter mining operation? To understand how this works, we have to look inside the flesh of the fruit itself to survey our hypothetical mining site. A typical banana contains about 360 milligrams of potassium. Most of that is completely stable, normal matter. Out of 360 milligrams of potassium, we isolate a tiny sliver, exactly 0.04 milligrams of radioactive potassium-40. Every 75 minutes, an unstable atom decays and breaks apart, ejecting a positron. This antimatter particle is the positively charged mirror image, the evil twin of an electron. That means the fruit sitting on your counter is a verifiable, continuously operating factory, churning out the universe's most precious resource day and night. To make this operation profitable, we need to scale up from a single piece of fruit to a planetary harvest. Let's run the math on the maximum possible yield. Assume we coordinate the simultaneous extraction of antimatter from every single banana currently growing on Earth. This map tracks that global harvest. Gathering the entire planet's supply of bananas and collecting every positron they produce would net you an abysmal return on investment, about 11 cents worth of antimatter per year. It is a terrible profit margin, sure, but mathematically, you have still successfully mined physical, real-world antimatter. The low yield isn't what bankrupts the operation, though. The true roadblock is what that antimatter naturally does immediately after it is created. If we drop back down to the subatomic level, we can track the positron the exact second it is born. This timeline tracks the positron emerging, surviving merely 1/10 of a nanosecond. Positively charged, it's instantly drawn toward a nearby normal electron. When they touch, they trigger quantum annihilation, violently destroying each other in pure energy. Zero physical material is left to harvest. The laws of physics effectively rig the game against us. The product self-destructs before a fraction of a second has passed, permanently foiling any attempt at an antimatter banana mine. Pulling back from that microscopic destruction, we return to the quiet surface of the kitchen counter. It is completely silent up here, yet that exotic dance of creation and annihilation is happening continuously right under our noses, completely unseen. Every 75 minutes, without fail, another atom decays, another positron is born, and another pair annihilates itself right inside this ordinary fruit bowl. The deepest mysteries of particle physics are not restricted to the vacuum of deep space or to billions of dollars in lab equipment. They are woven quietly into the fabric of our everyday lives.